Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is using an oscilloscope to measure and display current. Our objective is to learn how to indirectly measure and display a plot of current on an oscilloscope using a sensing resistor in Ohm's law. This lecture operates under the presumption the viewer has more than a passing familiarity with basic oscilloscope measurement techniques and can measure relative phase shift between two waveforms using an oscilloscope, as illustrated in the Measuring Phase Shift with an Oscilloscope lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. Can you use an oscilloscope to directly measure current? No. No, you cannot. An oscilloscope is not an ammeter in the traditional sense, but rather it is a voltage measurement device that will only display a plot of voltage across an element as a function of time. This being said, voltage, current, and impedance are related quantities via Ohm's law. Perhaps you've heard of it. Given current is voltage over impedance, one can easily calculate the current through an element given the voltage across it and a known impedance. While this technique does induce a bit of error because of some assumptions and simplifications made, it does yield reasonably accurate results, and importantly, allows current through an element to be displayed with reference to the voltage across it. As we've learned in previous lectures, relative phase shift between voltage and current is an extremely important property, and this technique allows a technician to experimentally obtain this data. Key to measuring and displaying current through an element of interest using an oscilloscope is the addition of a small resistor in series with the element of interest, known as a sensing resistor. Employed in this fashion, an oscilloscope indirectly measures current by measuring the voltage drop across the sensing resistor and uses the sensing resistor resistance as a scaling factor for voltage. As Ohm's law so reliably illustrates, current equals voltage over impedance. Essential to this technique is your understanding of basic series circuit properties. Current through elements in series with one another is the same, and the summation of all voltage rises is equal to the summation of all voltage drops. We'll examine basic properties of series AC circuits in later lectures. However, they're essentially a repeat of basic series DC circuit properties. Consider the following series circuit. Given a source E and a series path consisting of element X and a sensing resistor RS, it can be said that there is a single path for source current through the element and the sensing resistor. Source current equals the current through the element equals current through the sensing resistor. I source equals Ix equals IRS. Additionally, it can be said that this series path consisting of two elements is composed of a single voltage rise, our source E, and two drops. One, the voltage drop across our element, Vx, and two, the voltage drop across the sensing resistor, VRS. Given the summation of all voltage rises is equal to the summation of all voltage drops in a series path, it can be said that the source voltage E equals the voltage drop across our element Vx plus the voltage drop across the sensing resistor, E equals Vx plus VRS. For this technique to work with a reasonable degree of accuracy, one must choose a sensing resistor with an appropriate magnitude such that it doesn't unduly influence our observations. Regardless, the inclusion of a sensing resistor, no matter how small, will still induce a tiny error. Ordinarily, a sensing resistor with a resistance of, let's say, 1/10 the magnitude of the impedance of the element in question will provide sufficiently accurate results. The smaller you go, the less the sensing resistor will unduly influence the results. For example, if we wanted to measure current through a 100 ohm resistor, making use of a sensing resistor of, let's say, 5 ohms should give us reasonably accurate results, since the sensing resistor's magnitude is only 1/20th the magnitude of the 100 ohm resistor. Sizing a sensing resistor for reactive elements, however, necessitates a bit more thought, since the impedance magnitude for reactive elements like capacitors and inductors is a function of frequency. Consider a 120 millihenry inductor subjected to 60 Hz AC. The inductive impedance formula makes it clear that this inductor presents an impedance of approximately 45.2 ohms at an angle of positive 90 degrees. A 5 ohm sensing resistor might be a little too high for this application, since 5 ohms is only 1/9 of the inductive impedance magnitude at this frequency. Perhaps a 2 or even a 1 ohm sensing resistor might yield better results. If, however, we were tasked to measure current through the same 120 millihenry inductor at not 60 Hz, but rather 1.5 kHz or 1500 Hz, our original choice of a 5 ohm sensing resistor might be more than adequate given the inductive impedance formula makes it clear that this inductor now presents an impedance of roughly 1.1 kiloohms at an angle of 90 degrees. At this much higher frequency, the 5 ohm sensing resistor now only represents less than 1/200th of the impedance magnitude of the inductor. Additionally, one must ensure that the sensing resistor can handle the anticipated current draw. Long story short, do the calculations first. Recall that resistors exhibit no phase shift between voltage and current. That's why one uses a sensing resistor to indirectly measure current through our series circuit rather than a sensing capacitor or sensing inductor. This fact is extremely advantageous and frees us from any unnecessary additional calculations regarding phase shift. Deploying a sensing resistor to indirectly measure current necessitates the user confront a technical limitation of most oscilloscopes, even the modern ones, head-on. Most multi-channel oscilloscopes, unless explicitly designated as one employing isolated channels, reference all channels from ground. This means channel 1 is a plot of voltage with respect to ground, as is channel 2. This implies that the reference lead for both channels, ordinarily the small alligator clip dangling off the probe, is always hooked to ground. This isn't necessarily a deal breaker, however it does necessitate a user be aware of this fact and take the appropriate steps to avoid total disaster. We'll examine implications of this in greater detail in later lectures on series AC circuits. However, as a primer on this subject, consider the wrong way to employ a multi-channel oscilloscope in a series circuit consisting of our element of interest and the sensing resistor in series. This is the wrong way to measure voltage across two elements in a series circuit. Channel 1 is measuring voltage across our element of interest with respect to ground. Channel 2, however, is measuring voltage across the sensing resistor, where both terminals of the sensing resistor have been grounded. Given both terminals of the sensing resistor have been placed at the same ground potential, there will be no voltage drop across it. Do not do this. This is the wrong way to measure voltage across two elements in a series circuit using an oscilloscope. I will tie you to a goat and throw you in a hole if I ever see you using an oscilloscope in this fashion. This is the correct way to measure voltage across two elements in a series circuit using an oscilloscope. Channel 1 is measuring voltage across both our element of interest and the sensing resistor with respect to ground. If you think about it, channel 1 is basically measuring the voltage across the whole series circuit, essentially our source voltage. Channel 2, in contrast, is measuring voltage across only the sensing resistor, where only one terminal has been ground referenced. This is where the small error comes in. What if we were to assume the voltage drop across the sensing resistor, in comparison to the voltage drop across the element of interest, to be negligible? If we've appropriately sized the sensing resistor, this is probably safe enough to assume. Given this assumption, it can be said that all voltage will be dropped across the element of interest. Symbolically, we can represent this assumption as follows. Given our earlier exploration of the voltage rises and drops in this series circuit showed us that E equals Vx plus VRS, if we assume the voltage drop across the small sensing resistor is sufficiently minor in comparison to that of the larger element of interest, we can state that the source voltage rise is approximately equal to the voltage drop across the element of interest. While not entirely true, this assumption significantly simplifies the remaining calculations. Let's just go with it. Operating under this assumption, it can be said that all voltage will be dropped across the element of interest, essentially eliminating the sensing resistor from consideration. Using this assumption, the voltage across the element of interest is being measured by channel 1. What is channel 2 measuring? Channel 2 is measuring that tiny neglected voltage drop across the tiny sensing resistor. Mathematically, we are ignoring it. However, it's still there, and the oscilloscope screen can be appropriately scaled such that this voltage waveform can be displayed and measured. Given current is voltage over impedance, an appropriate scaling factor can be applied to the voltage on channel 2 to arrive at the resultant current. Additionally, one can simultaneously display both channels to show the relative phase shift of the voltage across the element of interest and the current through it. This is the principal advantage of this technique and the reason I demand students get good at it. Recall that ammeters and voltmeters customarily limit themselves to the measurement of effective magnitude only and ordinarily do not measure relative phase shift. This technique, however, allows a technician to determine the relative phase shift between voltage and current. Allow me to demonstrate. Consider a 10 microfarad capacitor subjected to sinusoidal AC with the following properties. It has an effective value of 4.1 volts and a frequency of 60 Hz. The capacitive impedance formula shows us this 10 microfarad capacitor would have an impedance of roughly 265.3 ohms at an angle of -90 degrees at 60 Hz. Additionally, Ohm's law shows us that this capacitor would be anticipated to draw roughly 15.7 milliamperes of current, and current would be expected to lead voltage by 90 degrees. Given these anticipated values, let's see if we can use a small sensing resistor in series with the capacitor to indirectly display current through it using an oscilloscope. Let's make use of a 5 ohm sensing resistor. Think about it. An additional 5 ohm resistor in series with an impedance with a magnitude of 265.3 ohms doesn't really change the total impedance all that much. We could do the calculations, but let's just ignore it. Assuming the current through this series relationship is unaffected by this tiny additional resistance, we can say the current through both the larger capacitor and the smaller sensing resistor is 15.7 milliamperes at an angle of positive 90 degrees. This, by the way, won't be true since the total impedance would be slightly different, yet we kept the supply voltage the same, but we're conveniently ignoring this fact. Operating under the assumption that the current is unaffected, Ohm's law shows us the 5 ohm sensing resistor would experience an effective voltage drop of roughly 77.3 millivolts at an angle of 90 degrees across it. This is a super tiny voltage drop. However, it's still measurable by the oscilloscope. If we place the voltage across the whole series circuit on channel 1, it might look something like this. Note channel 1's vertical sensitivity is set to 2 volts per division, and the horizontal sensitivity is set to 2.5 milliseconds per division. It looks like the voltage waveform on channel 1 has a peak-to-peak span of roughly 5.8 divisions. You note it's a little asymmetric in that the positive half seems to be larger than the negative half, but not by much. Regardless, at a vertical sensitivity of 2 volts per division, this corresponds to a peak-to-peak value of 11.6 volts. If we assume this waveform to be zero-centered, which it obviously isn't, an 11.6 volt peak-to-peak value corresponds to a peak value of 5.8 volts. A 5.8 volt peak value corresponds to an effective value of approximately 4.1 volts. Thus far, we seem to be tracking regarding our desired supply voltage. Looks like the supply voltage is a frequency of 59.8 Hz. This is close enough to our desired frequency of 60 Hz. Let's just go with it. When we display channel 2 simultaneously, also using a vertical sensitivity of 2 volts per division, we are rewarded with what may appear upon casual inspection to be nothing more than a flat line. Is this true? Is there nothing on channel 2? No, far from the truth. Recall channel 2 is measuring an extremely small voltage drop across a small sensing resistor. Only when viewed at the same scale of channel 1 of 2 volts per division does channel 2 appear to be a small ripple. If, however, we change the vertical sensitivity of channel 2 only, note channel 2 leaps out of the screen and screams, "Look, I'm leading channel 1 just like your calculations demonstrated." All we have to do now is measure it. Note channel 2's vertical sensitivity is now set to 50 millivolts per division. The horizontal sensitivity for both channels remains at 2.5 milliseconds per division. It looks like the voltage on channel 2 has a peak-to-peak span of roughly 4 divisions. At 50 millivolts per division, this corresponds to a peak-to-peak value of 200 millivolts. A 200 millivolt peak-to-peak value corresponds to a peak value of 100 millivolts. A 100 millivolt peak value corresponds to an effective value of approximately 70.7 millivolts. Recall our earlier calculations suggested we should be experiencing a voltage drop of approximately 77.3 millivolts across the sensing resistor. There is some error, but we're in the ballpark. More to the point, the voltage on channel 2, our indirect representation of current, is clearly leading the voltage on channel 1. By how much? Given channel 2 appears to be leading channel 1 by, let's say, 1.7 divisions, and our horizontal sensitivity is set to 2.5 milliseconds per division, this corresponds to a forward shift of roughly 4.25 milliseconds. Given a 60 Hz waveform has a period of approximately 16.7 milliseconds, a forward shift of roughly 4.25 milliseconds corresponds to a phase shift of roughly positive 91.6 degrees. We anticipated it to lead by 90 degrees. Our observations are super close to our expectations. Isn't that convenient? The phasor representation of the voltage across channel 2 can therefore be written as 70.7 millivolts at an angle of 91.6 degrees. Now, given we know the sensing resistor to have a resistance of 5 ohms, we can use Ohm's law to demonstrate that the current through it has a phasor value of 14.1 milliamperes at an angle of 91.6 degrees. Our observations are not that far off from our expectations. I will admit that there is some error using this method. However, you need to look at the larger picture. What we've done here is to simultaneously display the voltage across a component and the current through it on one screen. Granted, we're displaying current through an indirect means that does induce some error. However, we are clearly dealing with a capacitive element since channel 2, our indirect means of measuring current, is leading channel 1, our direct means of measuring voltage, by 90 degrees. Additionally, we can get a rough idea of its magnitude and the degree of phase shift. You'll note the small error springs from several sources. Principally one, our earlier assumption that the inclusion of a small resistor in series doesn't adversely influence the total impedance of our larger element of interest. 2, our assumption that the small voltage drop across the small sensing resistor is also negligible in comparison to the supply voltage. By the way, I'll show you in later lectures on series circuits how an oscilloscope can correct for this tiny error using Kirchhoff's voltage law and automated math functions. 3, the value of the sensing resistor itself. Note we're operating under the dubious assumption that the sensing resistor has a value of exactly 5 ohms. In truth, it might have a value of 4.95 ohms or 5.05 ohms. The point being that a tiny shift in resistance would also shift our calculated current. And finally, 4, differences in human interpretation skills. Is it 1.7 divisions or is it really 1.69 divisions? As your lab partner so ably demonstrates, humans come with varying degrees of perceptive and cognitive abilities and can only expect it to be so accurate. It should be noted, as we demonstrated in the oscilloscope measurement techniques and measuring phase shift using an oscilloscope lectures available at the Big Bad Tech channel, modern oscilloscopes often offer cursors and automated measurement utilities designed to assist in precise measurements and eliminate some of these interpretation errors. In summary, there is a lot of mathematical hoops the data on channel 2 needs to jump through to indirectly display current on an oscilloscope. This being said, it's really close to what we expected, and I am absolutely overjoyed to have this ability, even with its inherent flaws. Part of the reason this technique seems so contrived and unwieldy is all the calculations necessary to make it work. When you get down to it, the final calculation is a conversion from voltage to current using the sensing resistor resistance value as a transfer function. Luckily, some modern oscilloscopes, like the Tektronix TBS 1032B digital oscilloscope I'm employing for this lecture for demonstrative purposes, offer the ability to automatically perform this transfer function. To enable this feature, go to the Channel 2 menu. Choose Current rather than the default voltage. Note it initially assumes a scale of 250 milliamperes per division. This is obviously wrong since our current is anticipated to have an effective value of only 15.7 milliamperes. We need to find an appropriate scaling factor for our given 5 ohm sensing resistor. If you think about Ohm's law from the perspective of units, you know an ohm is a volt over an amp. Therefore, a 5 ohm sensing resistor is 5 volts over 1 amp. Or if you flip the transfer function on its head, 1 amp over 5 volts or 200 milliamperes per volt. When we select the appropriate scaling factor of 200 milliamperes per volt, we note channel 2 is now more appropriately vertically scaled to 10 milliamperes per division. Is the oscilloscope really directly measuring current? No, it's not. It's still indirectly measuring current, only it's automatically rescaling the small voltage drop across the 5 ohm sensing resistor using the chosen transfer function. Really, the only way to mess this feature up is to choose the wrong transfer function, which, by the way, happens pretty often because folks forget this feature necessitates an appropriate scale. You note other scales are available, including 1 amp per volt for 1 ohm sensing resistors, 2 amps per volt for 0.5 ohm sensing resistors, and so on. You note using this new vertical sensitivity, channel 2 is a peak value of 2 divisions high, where each division is now 10 milliamperes. This corresponds to a peak value of 20 milliamperes. A peak value of 20 milliamperes corresponds to an effective value of approximately 14.1 milliamperes, as we obtained previously. Note, current still leads voltage by a relative 90 degrees. In summary, the ability to rescale channel 2's voltage input as current with a specified transfer function takes at least one tedious calculation out of the picture. While not an absolute necessity, this feature sure is handy.